Hello, welcome back. In the last lecture, we have introduced the basic structure of a MOS capacitor, and then we defined what is accumulation, what is depletion. Today, we would like to understand a little bit more about this depletion and accumulation regimes, and we will do that by drawing band diagrams. So the band diagrams I'll be showing you today will be simplified band diagrams. We will actually draw the complete band diagram in the next week. But for now, let us consider what's the basic MOS capacitor, NMOS capacitor. So let's say we have a substrate which is P-type, and then I want to there's an oxide, and then there is a metal on top. And this is gate, and this is an oxide. Okay. Now I want to draw a band diagram as I go from the top to bottom. So along this axis, I want to draw a band diagram. Okay, let's say this is X. Okay. So how would it look like? To do that fully, we need to look at what are the Fermi level of the gate, what is the band gap of the oxide, and then band gap of the silicon. Right? We have to take everything into account. That would be a full and proper thing to do, and we will do that in the next week. But before I do that, today I want to focus only on the bands in silicon. Okay? So that's why I call it simplified band diagram. Okay. So what I'll do is I'll try to just flip it, and then I'll say I'll have a gate, and then there is an oxide. Okay, so this is my gate, and this is my oxide. And for now, I don't really want to bother about what is there in oxide and gate. Okay? We will look at it later. For now, I want to just purely look at what is happening in the semiconductor. So what I'll do is I'll draw the bands of a semiconductor. Okay. So this will be my EC, EV, and then there is a Fermi level, right? So where is the Fermi level? For a P-type semiconductor, it should be closer to EV. So there should be a Fermi level here, EF. Okay. So what essentially I'm drawing is, this is X-axis. Well, I mean, by X I mean from top to bottom, right? Let's say that X equal to 0, this is the interface. And then, so this is your X equal to 0 is a gate, silicon dioxide and silicon interface. Okay, this oxide will be silicon dioxide, right? In most of the cases, for now. Okay, so now we want to draw this band diagram. So this is essentially without any applied bias, nothing much happens, right? We are not really worried about Fermi level in the gate right now. We'll assume that it's exactly the same Fermi level as the substrate. So we are not even showing it. So now this is at 0 applied bias. What happens as I apply a gate voltage? Okay. So if I apply a positive gate voltage, what do we expect? So if now this is VG, and there is of course there's a counter terminal in the substrate. Okay, we're not showing, this is like semi-infinite in the substrate. Okay. So now if I apply VG greater than 0, what did we say? We said that if gate voltage positive, then that's going to drive the holes away from the interface, silicon dioxide interface, and then that will create depletion. How will we represent depletion in a band diagram? Well, let's draw it one more time. So let's say this is your metal. Let's say there is an oxide. I'll call it SiO2, and this is Vg. You're applying on this, and now it's depleted. So what we have to do is, let's ignore the interface for a moment, and then just draw the bands in the bulk. Okay. So where you should have an EF like this. And whatever we did, if you apply positive voltage, it's not going to drive all the holes out of the semiconductor. It's only going to drive some holes out till you uncover the exact balancing charge. Let's say this is positive Q, right? It will uncover some charge in such a way that there is the balancing minus Q on the semiconductor side. Okay. So it is depleting in the surface. So how will we show depletion? Well, Fermi level still it's under equilibrium, so this has to be this, right? There will be some shift in the gate Fermi level. We will deal with that later. Okay. So now, since we are depleting, the bands have to bend downwards. This is how you represent the depletion. And so this distance, I can call it XD, the depletion width, or X depletion, XD, which is essentially the depletion width. If you want to call it W. Okay. Textbook calls it XD, so I am using XD. Okay. So what is this? This is the depletion region. And how is the charge looking like? If I ask you to draw the charge profile of this as a function of X, space charge profile, right? So I can take my, this is my X, this is my rho if I want to draw. It's a P-type semiconductor. We have, well, I need to push this up slightly. This is my P-type semiconductor, and then I want to draw as a function of X. So when I apply positive voltage, what essentially I'm doing is at the interface, I'll call it, this is X equal to 0 is an interface. So, and then I'll take some thickness, this is some thickness, Tox. This is oxide thickness. Okay. So, and then there is metal here, all this is metal from here onwards. It's all metal, right? So when I apply positive voltage, I get some charge here. Okay, this will be plus Q. Okay, which is on the gate, right at the interface between gate metal and then oxide. Okay, and as what happens in the semiconductor? Semiconductor is depleted, but it's a space charge, right? It's going to have a uniform density here. So this is my depletion width. And this will be my NA, right? The doping density times the XD will give you the total charge. So Q positive, right? Or Q is going to be in magnitude, it's going to be equal to Q NA times XD. The total amount of depletion charge, right? Well, depletion charge is negative, so on the positive side you have this, okay? If you want to write Q depletion, then you need to put a minus sign here. Okay. So this is my bands when I am in the depletion regime. What happens in the accumulation regime? Okay. For accumulation regime, we said that it's a P-type semiconductor in the substrate. So if you want to have more holes, you need to put a negative voltage on the gate. Okay. So what I'll do is VG less than 0. So what happens now? Again, the same things. I will just draw oxide, SiO2 and gate VG, and then there's, let's say there is Fermi level here, EV and then EC, and there is a EF. Okay. So now, since we applied a negative voltage, VG is less than 0, it should have more holes at the interface, right? Accumulation. How will you represent more holes at the interface? Well, the Fermi level is still the same since it's equilibrium. Now, the bands will bend upwards. Okay. This is indicating holes are more at interface when compared to holes in bulk. So please make sure that you are convinced about this by looking at this band diagram. I mean, it's obvious because here, this is the distance, right? If EF is closer to EV, it has more holes, right? So when you compare the distance of EF and EV, it is more in the bulk and less in the interface. So you have more holes in the interface. That's why we call it accumulation. Whereas here in the depletion regime, EF is farther from the EV, so you have less holes here. Or rather, you depletion of holes. We removed holes from there. What you have left is some space charge. There are no holes present anymore there. It's completely depleted. Well, almost completely depleted. Okay. So this is the difference between accumulation and depletion regime in terms of band diagrams. And these are simplified band diagrams, mind you. Okay. So let me show you this is my picture. So I hope, it helped you understand the process of drawing these diagrams. I'll quickly show you the result. Okay? This is from the textbook. You could read up a little bit and then understand if you are unclear about something here. So the same thing that we have been talking about. So if you have zero applied voltage, your bands are flat, EC, EV, EF, and so on. Okay. Now, if you apply negative gate voltage, you have accumulation of holes here. Okay. And if you have positive gate voltage, we have depletion of holes. Okay. So this is my depletion. This is my accumulation. I'm sorry. Okay, it's written here. So accumulation of holes, and then there's no applied voltage. There's nothing much happening. So these are the accumulation, depletion, and primary modes we have talked about. Okay. In the next video, we will just talk about what is known as inversion. Okay. Inversion also is another important property, and that plays a very, very crucial role. That's why I want to talk about it in a separate video. All right. So I'll meet you there. Thank you.